So for problem number 49, it says in exercise 48, suppose instead the case had been properly wired and grounded as shown in figure 23. If the grounding wire had a total resistance of 0.10 ohms, what is the ratio current in U to the current in the ground wire, assuming that the fuse/circuit breaker does not trip? So in problem number 48, it's talking about not having that additional dedicated grounding wire, and you go through and you crank through the math and see it's not good if you have a problem. So to solve this problem, what we're going to do is we're going to use Ohm's law. All right. So we know that V is equal to IR. And so we're asked to figure out what is the ratio of the current in U to the current in the ground wire. So if I use Ohm's law, I get that the current is equal to the voltage divided by resistance. So the current in me over the current in the wire is what we're calculating. All right. And then this is an extension of problem number 48. And 48 just said it's a household wiring. So the voltage, is going to be 120 volts. And they also give us some information. So the resistance in U, so let's write this out. The voltage in U over the resistance in U all over this thing here, all over the voltage in the wire, all over the voltage, or not the voltage, the resistance of the wire. And so in problem number 48, they said that the resistance in U is about 300 ohms. Okay? And then the resistance in the dedicated wire, this right here, is 10 ohms, or 0.10 ohms. And I think the voltages will cancel out. So anyways, what you end up with is we have 120 volts all over 300 ohms, all over 120 volts again, all over 0.10 ohms. And I think if you do the math, the 120s will cancel and you'll get, like, if you do significant figures, you should end up with 3.3 times 10 to the negative 4 amps. And so that's the ratio from U to the wire, which isn't bad. So this is part A. Now, part B wanted to figure out what the current would be going through the dedicated ground. I didn't write it up there. So part B is, what is the current going through the dedicated ground? All right, well, that's pretty easy. So we said that I is equal to the voltage divided by the resistance. So I've got 120 volts divided by 0.10 ohms. And by the way, this is a significantly small, I want to point out that this is a very small number. So you have almost no current, nothing that will hurt you. And this would to give you an idea of how much of it's going through the dedicated wire. If you do the math on that, that's 1,200 amps. Okay. But in a house, that'll definitely trip a circuit breaker. So I also think Part B, if I remember correctly, says, will it trip the circuit breaker? Yes. It'll definitely trip the circuit breaker. Because circuit breakers in a house, I can't remember if problem number 48 said it was a 20 amp service or a 30 amp or a 15, but usually in a house, it's not much more than that. And so this is more than enough current to trip that. Okay? So that would be the current going through. And so if you compare the current going through the grounded wire compared to you, it's a very small current. It's like 0.000. So if I wanted to rewrite this, this is the same as 0.003. 1, 2, 3. I think there might be another zero in there. 1, 2, 3, 4. Yep. Amps. And that's comparing you to the wire. Now you still have some current going through you, but when you compare the two, it's a very small amount. So this is not what is you. You is this divided by this, which is a much smaller number than. So this is you, and if you did the math on that, it'd be roughly about 1/3 of an amp, or 0.3 amps, which a human being can handle that. Not for too long of a time, but it's pretty small. And then if you compare the two, the ratio between you and the wire is this number, and then this right here is how much current is going through that dedicated ground wire.